Hello and welcome to this video. Today we're going to be talking about why 3D UTAPWeLS. UTAPWeLS, as you know, it's a software that's been around for 15 years, 20 years, something around that neighborhood. And even though most users understand why you use it, or at least some aspects of it, I thought now that we have 25 years of the Formation Evaluation Consortium, it was a good time to revisit why we're doing it and probably get some of you to join the user base, and those that are already using it, think about the other uses that you can give it, how you can incorporate it in your workflows, and what can you do with it. Now we're going to start from the beginning. UTAPWeLS, or 3D UTAPWeLS, stands for the 3D University of Texas at Austin Petrophysical Well Log Simulator. And really what sets it apart is that we work with an Earth model. An Earth model, as it sounds, it's exactly what it sounds like. It's a model of the subsurface Earth, the different properties that you may have, the porosity, and so on. And from an Earth model, one of the key things that you can do with UTAPWeLS is you can do some calculations with it and some simulations, especially tool simulations, well logging simulations that will give you something similar to field data. In that case, it would be simulated data. And in a good day, it'll be very close to your field data. And that's going to be the key of this. We're going to try to get Earth models that are as close as possible, or that reproduce the field data as close as possible. And then we're going to use the properties in the Earth model to do any evaluation afterwards. Any monetary evaluation is going to be coming from that is going to be a lot more accurate. In some cases, the Earth model and the field data are going to be very close. For example, if you have a single layer that has no variation whatsoever, when you log it for porosity, that porosity is going to be probably the real porosity. The resistivity is probably going to be the real resistivity, and so on. But there's a number of cases where that's not going to be the case. So when can we say that using the field data directly as if they were physical properties is correct? And when is that not correct? And this is probably the core of the question, why UTAPWeLS? With that workflow in mind, Earth model to calculations and simulations to field data, we're going to think about cases, for example, due to formation or borehole effects. For example, if you have thin layers, the field data is not going to be a true reproduction of the Earth model because you have shoulder bed effects. Also, if the trajectory is deviated, you're probably going to be off because the tools are measuring layers that are different than the layer that you're thinking. They're going to be measuring a combination of layers similar to the shoulder bed effect, but different, slightly different. Also, if you have laminations or if you have anisotropy, same case. If you're in a gas-bearing formation, famously, that you might not be getting it right. And of course, there are some corrections that everybody knows how to handle, but you can get it more correct if you start from a physical model, an Earth model that honors all possible measurements. Also, similarly, high salinity is complicated. If you have mud cake or filtrate invasion, that's going to modify the way the logs look compared to one that is not invaded. So if you have invasion, what do you do to get as close as possible to what you want to the properties that you want? So the virgin zone, for example, knowing that many of the measurements, because of the depth of investigation, is going to be affected by that invasion. So you model. That's the answer. Similar, if you have washouts or if you have buildup, you can mitigate that using UTAPWeLS or using through modeling. Also keep in mind that in many cases we do indirect measurements. So we never really measure water saturation. In most cases, we just assume that the resistivity is going to tell us what is the water saturation. Do we know that that model is correct? This is going to help us. Similarly, porosity, we usually get it from neutron or density logs. Is that actually correct? Does it honor every measurement? So permeability, it's a whole other story with a combination of measurements that usually we try to honor and true expertise from people that have been in the field for a long time. And all this is going to be related to the rock physics models. Famously, we are just used to using Archie for all scenarios, knowing that if there's significant shale and the shale is conductive, is not going to be right. We don't care. We keep going that way, knowing that we're getting the wrong answer. And then we correct afterwards with some, well, we compensate here and there. why don't we start from using the right physics model? That's one of the things that we're going to be able to do with UTAPWeLS. You can do it in other places, but UTAPWeLS is centralized and it has all these options already built in. Similarly, sonic models, we can go beyond the heuristic models that we always use. Same with shale mineralogy. Instead of staying with single shale that has properties that are not all that clear, we can make sure that all properties are honored by the shale, the design of the shale that we're going to be using. And really, all these things that I'm mentioning here are things that are going to affect how the Earth model turns into field data. But in reality, what we want to do is, starting from field data, we want to get back to the Earth model, to the true petrophysical properties. And that's what we call inversion. And that's another thing that UTAPWeLS can do. All these are the reasons. In summary, this is the slide that I wanted to present today. A very typical sample resistivity workflow that we've presented for probably the whole 25 years. It's suppose that you have a thin layer. When you measure it, you get the log response that looks something like this. If you were doing what we call the poor man's modeling, you would just say, okay, there's some shoulder bed effect. There's 3 layers, and the one in the middle has higher resistivity than the one on the top and the bottom, and the resistivity is going to be this. You're going to be better off than if you just take point by point. But you're probably not going to be completely correct. If you take this model, this blocky log model, and you ran a simulation on it, you would see that you're undershooting. So you could probably say, well, actually, what I need to do is I need to modify the resistivity to something larger in this layer. And then if I run the numerical simulation, it's going to match the field log. And then that's going to be the UTAPWeLS interpretation that, of course, is a lot more accurate than what you would have done with a conventional interpretation modeling, and more accurate than just taking the log. Now, going a little bit more into the Earth model, what we talk about, what do we mean by an Earth model? In few words, it's a piecewise constant set of properties in layers around the well. Suppose that you have a well that has fairly horizontal layers. In the model, they're going to be 100% flat, not horizontal. They can have a dip, they can have an angle, and the trajectory doesn't need to be straight down, but it's good enough for what we want to show. Anyway, so to each layer, we're going to assign a property. In this case, it looks like its density just by the values, but this is just a numerical array of properties, each one corresponding to a different layer. And this is going to be the most basic model that we can talk about. Is just a specific number for a specific property in each layer. We can get a little fancier with the geometry, and we can say there's if we look at the borehole from the top, there's going to be radial zones around it. This is, of course, interesting in cases where we handle invasion, mudcake invasion or filtrate invasion. And in that case, for each of those, we're going to have a number. It's going to be constant in none of those. There are certain constraints. For example, porosity, we assume it's not changing, but resistivity may change. Anyway, now digging into the way the software looks, I'm not going to go too deep into the software. This video is also meant to be just a quick invitation, and we have a series of videos that are the crash course. This is kind of chapter 0 for that crash course. So it's a very quick overview. Don't expect me to go too deep. We have those other videos, and you can always shoot me an email. So from the main window, you can load and save projects, as you could imagine. You have project notes if you want to write anything specific to that project. You will handle the settings, where you would decide how the computer uses the resources, the viewing options, the colors, and so on. You can explore the project. You can see the different logs, the different wells, some values for each of the wells, each of the logs and the wells, the depth range, and so on. You can also, very importantly, add wells and access the different wells. And if you access any of those wells, we go into the window where you will be spending most of the time. We call it the well interpreter. And this is where you would view the well data. It's always the tracks are present. It's very easy to view predefined views. In this case, I'm just using the triple combo, and it shows you gamma ray, resistivity, neutron porosity, density. And it's very easy to predefine that. It's very easy to have certain mnemonics so that regardless of the name of the curve, If you have defined it in your mnemonics, it's going to show there. Each company has specific mnemonics. It's very easy to manipulate them and modify them. And if you have questions, you can always ask. It's a place where you can also make quick plots. You can make histograms. You can make cross plots very quickly. You can make and view data selections. Those selections are going to be relevant because it's not just selecting some segment and viewing it in cross plots, for example, or other places, but you can also select that and use it specifically for certain calculations or for some analysis. You will also be able to manipulate the Earth model here. You can plot the specific properties and you can add layers, you can delete them, you can manipulate the properties and so on. And very importantly, you can access all the modules that you're going to be using for that specific well. In general, one of the most common ones that you're going to be using are simulations. Say you define a resistivity model that looks something like this. You open the resistivity simulator and you decide which tool and variant, so on, and it will give you the curves, how the different curves would look like, the tool response, given that you have a specific model. Very similarly works for sonic, very similar for nuclear, all the nuclear logs, gamma ray, density, photoelectric. And we can also do inversion, not just simulation, but the inversion. Suppose you have some log that looks something like this, clearly thin layers, clearly two different sets of types of rock, one higher resistivity than, or in this case, neutron porosity, one with higher neutron porosity than the other. And if you just did the quick population, it would look something like this. Here you just define which logs are supposed to match which logs, which field logs, simulated logs. You run the inversion, you would be able to match those, get a better idea of where that neutron porosity would be in those cases, which in thin layers, not surprisingly, it's further out than where it was. And not only that, but you can also estimate the uncertainty intervals. So confidence intervals can also be part of that output. So you have even better formation evaluation, you make better decisions with it. You can also invert for piston-like invasion in case you have a separation of resistivity curves and you want to assess how deep is the invasion. You can do that here. You can export the results. You can view those results the usual ways. We have a table that is very easy to manipulate and decide which properties you want to see, which logs you want to see. And then you can save that as comma separated value, which is basically Excel, or you can open it with Excel. You can save it to LAS. It's very easy to export this, and then you bring it back to whichever program you use for the bulk of your work. We also have the palette, which is a very highly detailed view of the petrophysical properties that you have. So for any layer, you can see the porosity, shell concentration, and so on, the shale composition, matrix composition, and you can not only view it, but manipulate it and then export it to other layers. The fluids, and you can see some properties being calculated here. This is one of the original modules. It's been evolving. It evolves every year, but it's one of the main reasons why we started with UTAPWeLS. You also have goes hand in hand with the composition designer. Is something that this is a much more recent development. It's been around for a couple of years, maybe just 1 year actually. And it tells you something very similar to what the palette, but with a little less focus on how it's organized and a little more focused on the properties themselves. So you can see the combination of photoelectric, neutron, gamma ray density, and all these properties. When you mix them with different fractions, how that looks like. Something else that we have in UTAPWeLS is we have the petrophysical joint inversion. What this does is it takes some properties, for example, gamma ray, photoelectric, resistivity, some properties that are related to logs 1-to-1, and then it calculates porosity, water saturation, shell concentration, permeability, and so on, properties that will help you. Basically, it does formation evaluation, combining the physical properties and giving you petrophysical, what we call petrophysical properties, which are the properties that you see here. That's one of the newer modules, and it can be pretty powerful. We can also perform NMR calculations and simulations. We can estimate NMR porosity, And you can design any NMR sequence, which is something that some of the high skill users have done in the past. We also have a module that does invasion. It performs a simulation that, given a certain time, given PCKR curves, and giving all these high detail models that we have, will simulate how the mod is going to invade the formation at different times. We have also a formation testing simulation that is actually the same simulator, but focused on formation testing. We also have a set of UDAR modules. You can build coarse models, you can view them in the horizontal track display, and you can perform inversion for UDAR models. Talking about places where what you're measuring is very different from the property that you're actually interested in. UDAR is basically useless. You would never use the resistivity logs, even though the tool is very similar to any induction array tool. You would never just look at any one measurement and say, okay, this is the apparent resistivity. You need to really perform the inversion and estimate the resistivity at different distances from any of the measurements, and you need to combine them all. We have the capability of performing this inversion and forward simulations for 1D and 2D. We're working on the 3D. We have done this with field data and so on. Something else that is very useful for UTAPWeLS is scripting. And scripting is just the capability of writing any workflow in MATLAB. Well, we have a mini language that allows you to populate properties, that allows you to simulate logs, to modify any property of the Earth model or the rock physics model itself, and then see what that looks like after you run a simulation or a calculation. This is great for sensitivity analysis. This is great for when you're trying to test multiple different scenarios and you're not sure which one to choose. This is great. Also great for making sure that whatever you do is 100% reproducible. And we have all this within MATLAB, and we have limited access through Python. We're working on expanding the Python access, but the MATLAB access is thorough right now. Last, as just final thoughts, the way I see UTAPWeLS is as a playground for testing different hypothetical scenarios, and I hope you can see it that way. I hope it's a tool that you can use to test all the different possibilities that you think may be happening in a well, and you get to choose the right one. According to AI, this is how a playground for well log analysts and petrophysicists look like. So I hope you get as much fun as those little people look like they're having fun. You go down the gamma ray slide and you go across the resistivity bridge, the resistivity bridge, and all the good things that you can do. And at the end of the day, I hope this helps you solve models for many challenging scenarios that translates into better formation evaluation, because that's really what we're trying to do. And with that, I just want to say happy modeling, and I hope to see you around.